Okay, so we've run into a bit of a snag previously since I'd left IPv6 enabled, and chances are you're not going to be seeing this. So I've just disabled that for the machine that I'm using right now. We're just going to close this capture and start the second part of the exercise again. So we're capturing off ETH0 again. We'll just start the capture there and refresh this image again. So we're doing the image download in the second part of this assignment. I'm just refreshing. As you can see, it's downloading this again. That's completed, so we're just going to stop the Wireshark capture. From the DNS lookups we did earlier, we know that this address is the web server. So chances are all of this is part of that particular image download. So we're just going to save this capture as well. I've named the previous one IPv6. I'm just going to remove that designation from this particular one and save that. Yeah, this is also a fairly large capture just because the image itself is about 1.2 megs. So there's quite a large number of packets that need to be transferred in order to get the entire file downloaded. So we look at the third example, which is basically just sending an email. I'll load up Thunderbird, which is an email client, and send from an unrelated domain, which is strauss.nomza. We're just going to send an email to spam@hstrauss.co.za. So whatever we need to write in here. As yet, we've not connected to the, or sent anything across the network, so we still need to fire up Wireshark. Just typing that there. So we close this capture and we start a new one. Again on F0, let's start that trace. See something still going on in the background here. Just kill those. I'll stop that and start a fresh capture. Okay, so that's a lot less noisy. Cool. This message we're about to start sending, so once we hit send, we'll see there's a bunch of connection things in the background. There's a certificate mismatch, so we have to resend this, but that just means we'll have more traffic to capture. It's now connected, delivering the mail and sending it along. So that's all that we need to capture for that particular example. You'll notice that it was sending through a host telemail.com. That is the one that ends with .200 here. So all of this is captured within this trace. And we'll just save this as part 3. Last time we didn't compress it with gzip, but yeah, it might have done that implicitly. So we'll just, either way we'd be able to open it up with Wireshark again. So we now have the 3 captures for the assignment. So we can start having a look at some of the questions as we see in the particular assignment sections for DNS, TCP, and IP, and all the rest. If we look at the section 3, tracing DNS with Wireshark. We'll open up the first capture because we're talking about the DNS queries. So that would be the P1. You'll notice there's quite a bit of traffic within this session, and it becomes interesting to try and eliminate or find the little DNS packets in the middle of all these queries. One thing we can do is to use this filter box at the top. Either we can type an expression, and these you pretty much learn the more you use Wireshark. So I could do something like IP address equals the DNS server. We'll see that still doesn't filter everything because there are other queries coming from that box. Otherwise we can clear this and use the expression builder, and this basically allows you to select from a large number of protocols and match particular aspects of those protocols. So way down here at the bottom we see there's a DNS application, and we could use any of these to filter specific kinds of DNS queries. But what we're going to do is just use something that's available in all DNS packets, which is DNS.id. It's the transaction ID for each request that you're sending. We're just going to say if that is present, then it is implicitly a DNS packet. So once we filter on that, we only have DNS traffic. So looking at section 3's question 4, where it says locate the DNS query and response messages, are they sent over UDP or TCP? Naturally we could select any one of these, and we look in this bottom frame over here. So we see there's 5 expandable sections, and these roughly correspond to the OSI model, and it goes from layer 1 down to 2, down to 3, down to 4, and so on. Sometimes applications span multiple layers, or multiple applications are contained within a single layer, but in essence it's basically just hierarchically from the lowest level, so layer 1 down to the application layer, which is there. Since the question is if it's sent over UDP or TCP, we know that that would be layer 4, so this is where we're looking, and this one specifies a user datagram protocol, which is the full name for UDP. So we know that these queries are being sent over UDP. As an alternative, if we clear this and have a look at something like, okay, well there's a TCP stream for network share, and this one we can see is using Transmission Control Protocol, or TCP. If we look at question 6, for example, it asks to which IP address is the DNS query sent. So we can just have a look at DNS ID again. So we're looking for a query, not a query response over here. That's a query response, that's a query. So this query is being sent from 172.16.0.5, which is my local machine, to 172.20.0.20, which is the DNS server. Question 7, for example, says examine the query message. So we can look specifically at the query in more detail if we expand the application layer. So here we see the DNS ID, which would be 0x990. By selecting it, there are a number of options within Wireshark where you could actually convert this from hex implicitly, or within the interface of Wireshark. It's not really necessary at this point because we're not going to do too much with the transaction ID. But the question asks, what type of DNS query is it? So if we have a look at the query section, we see that it lists hstrauss.co.za type A. So this tells us that the query is for an A record. We can expand that even further, but as you can see, all of this is really summarized in the line above. So the more you expand, the more redundant the information becomes, but also the easier it is to read. So, for example, we could just expand that from the UDP packet itself. We only know that it's got a length, and it's destined for port 53. We can't see much more than that. But once we dig further into this, we can see the specific flags within the packets that are being sent, or the type of DNS message, or the exact query parameters. If we have a look at a response, we'll see something very similar, where there's a bunch of flags that have been either set where there's a 1 or not set where there's a 0. The number of questions is 1, the number of answers is 2. In addition to the answers to the question, they've also included 2 records which refer to the name servers. And then in order to save lookups, because they've already got the answers, they've also included additional resource records. So if you look at the additional records, this is basically the A record for the name server. So NS1 is located at 69.164.209.63. The authoritative name servers, we know these are NS1 and NS2. That's pretty much the type of questions you'll get for the DNS section. If we have a look at the bulk transfer, which in our case we did a download, they ask questions, so let's just open up that trace. We'll do the IPv4 one. So you'll see the filter remains here, and sometimes you'll forget to clear this and completely miss the useful parts. So even in this case, because I've only firewalled off the IPv6, it still attempts to connect to that, but then gets a message saying IPv6 is not allowed. It then retries using IPv4, and this is really the part of the conversation we're interested in. So it asks, what is the IP address and TCP port number used by the client computer? So in this case, this is going, so here we see something going to port HTTP or port 80 that sends a SYN. Then there's a response from 185.35.77.77 back to me saying this has got the SYN and the ACK flag set. Then after that we've got my IP address connecting to the web server, and it's got an ACK flag set. So these 3 packets form the TCP 3-way handshake. Once that's done, the actual request is sent from the client computer to the server, and the content of that is basically get this image. But referring back to the question, they're asking what is the source IP address and port. So we could either try and look at it from here and see that it's 58832, because that's the outgoing port and that's the incoming port on the server side. Or we could just look at either the IP or the TCP sections down below. So naturally, the source and destination IPs are handled by the IP layer. So there we can see the source. The ports themselves are handled by either TCP or UDP, so that would be the next expandable section. And in this case we see again, the source port is 58832, which we've seen above. The other question is what's the IP address for the server itself. From here we can see that the source and destination are specified in every packet that gets sent. So if I know I'm the source at 172.16.05, the other one is the server that we're looking for. Okay, the TCP workshop is just slightly different from this in that you use slightly more advanced features of Wireshark, but that's all explained within the assignment. So this is just to get you familiar with the Wireshark interface. Yeah, this interesting thing to note here is because Ethernet has a maximum segment size of usually around 1500 bytes, 1500 bytes, and this image, if we have a look at it, is 1,200,000 bytes. It's roughly about 800 packets, 800, 900 packets that need to be downloaded. So if we look at the time column, from the time we started the trace at 0, we didn't do too much on this for a while, and then around 17 seconds in we started trying to connect to the HTTP server. It then basically sent packets for quite a while. I think there's 1700 packets in total over here. Yeah, we see a bit of an interesting thing in that clearly something was either lost or retransmitted. So we get duplicate ACKs, which seems to suggest that the servers resent multiple parts, or resent a part multiple times, or the windowing made it only accept part of the transfer from the server at that particular time. And then near the end,